Properties of the definite integral. So again, idea-wise, a definite integral looks at the area under the curve from the left bound or the lower bound to the right bound, upper bound. Usually goes lower to upper. We're going to find sometimes they flip them. So from one number to the other number, and it finds the area between them. Okay? That area can be seen as an accumulation of change of a function. How much have you changed when you went from A to B? So I used an example myself. As a 3-year-old, I had a certain weight. And then as a 7-year-old, as a 9-year-old, I weighed more. So I would have a weight gain. And that would be my area under the curve would represent that. So some properties of our definite integrals. Does it make sense that if you go from the same number to the same number, if you go from 3 to 3, right? How much did you weigh on your 3rd birthday? And then how much did you weigh on your 3rd birthday? What was the difference? It would be 0 because there's no area under the curve from the same number to the same number. The area from A to B and the area from B to A are exact opposites of each other, right? If you've gained 50 pounds from age 3 to age 10, if you're looking backwards, age 10 back to age 3, you'd have to lose 50 pounds, or you'd be 50 pounds less. So we've got a negative involved there. If you went from A to B and there was some C value in between, does it make sense that the area from A to B is the same as the area from A to C and then C to B? With our weight example, if my change in weight from age 3 to age 10 was 50, my change of weight from age 3 to age 7 was 30, then 7 to 10 would be 20 more. If you have some constant, just like summation, just like derivatives, you can keep that constant inside or you could pull it out. So anytime you have a number, you could pull that number out in front. And we've already seen this with indefinite integrals, that you can take if you're adding or subtracting, not multiplying or dividing, but adding and subtracting, you can do the integral of both of them separately. So these properties, sometimes we have to use them to manipulate equations so that we can solve them. So here is our first example. You know that the area under the curve from 0 to 2 of f of x is 4, from 2 to 5 is 12, on g of x 0 to 2 is negative 3, and on g of x 0 to 4 is 6. So using the properties, can we figure out what this is equal to? So basically what we want to do here is use our properties to get these things at the top exactly as we see them. So what can I do in this situation? Well, I could say, since I'm subtracting, I do both of those separately. That's property number 5. And right away, I'm going to put a little happy face above this one. Because you see, you already know what that is. Because it's exactly what we saw before. This one has a 3 inside. And none of these up on the top have a 3 inside. But that 3 inside you could bring out in front. And now both of these you should be happy. Because you know the integral from 0 to 2. And both f of x and g of x. So now we can substitute in. It's going to be 3 times 4 minus a negative 3. And we can solve it from there. So I sort of feel like these are a little bit like puzzles. Can you figure out ways to get the properties to rearrange to make them work? So I want you to try the, since they're puzzles, puzzles are fun. Try the next board. I'll put up the answers in a bit. All right, I'll show the answers for the first two to see if you were on the right track. Good. So going to the same number is going to be 0. And since this is 5 to 2, you can change it to negative to make it go to 2 to 5. And C, we don't have 0 to 5, but we have 0 to 2 and 2 to 5. So we could break it up that way. And then we know it's 16. So we know the area from 0 to 2 was 4, the area from 2 to 5 was 12, or the accumulation of change from 0 to 2 was 4. The change from 2 to 5 was 12, so you could just add those up and you get the change from 0 to 5. How many people are done D already? Couple, but not a lot. I'll give you some time then. So in D, from 2 to 4, well, you know that you have 0 to 4, and 0 to 4 will equal 0 to 2 plus 2 to 4. Now, if we insert the values, we know this was 6, this was negative 3. So we can just move the 3 over, and that tells us the change had to be 9 from 2 to 4. Yes.
I had a different method. I got the same answer,
Mm-hmm.
but I took, what was it? Here, I took g of x, 0 to 2,
Mm-hmm.
g of x, and then I just used
The flip one.
and then that became negative, but since
It's the same idea. And that's the same idea of, had you moved this over early, right, it would make it negative on this side, which would be the flip of it. Now, what makes the last one a little bit tricky here is that you go from negative 3 to negative 1. So our initial thoughts are, I have none of those numbers on my givens. What am I going to do? But in an analysis of this, f of x plus 3, if you think back to your transformations, that would move your whole graph 3 units to the left. So if my area between, say, 2 and 5 was 10, and I moved that whole graph 3 units to the left, now that area between negative 1 and 2 is still 10. Because I just shifted my graph over, but the area under the curve, if you're moving it left and right, would not change. So we could bring that half out in front. That's one of our properties. Then we can apply the shift. If this is moved 3 to the left, we can move it back 3 to the right, and that would be f of x. So this area between negative 3 and 1 is the same as the original function's area between 0 and 2. So this is the idea. This area in green under here is the area between 0 and 2. Had you taken this graph and moved it three to the right, do you see that it now is between -3 and 1. But the area under that curve is obviously exactly the same as it was to begin with. So what we're doing here is we're saying, since this was a translation 3 to the left, I can get rid of this f of x plus 3 by moving it back 3 to the right. That's just going to give me f of x. That's going to add 3 to both of those, giving me 0, 2. That was on my list, and it's going to be 2. I think I have the picture here. Yeah, so I'm going to just... Yeah, I already drew the picture. We don't need to draw it again. So I use the property of integrals to evaluate the following. First of all, I'm going to tell you that from now on, you probably won't show this first step. The adding and subtracting integral property, for the most part, you'll just know you can do the integral of each one separately. So, whereas here I wrote it separately and then did each of these, moving forward, you will probably go right to the square brackets right away and go from 0 to 1 and have x to the 4 over 4 and e to the x. That's probably what you're going to do moving forward. But right now we're working on the properties. So we say, well, we could do each of them separately. And then after you've written the square brackets and done the integral and showed the bounds from 0 to 1, now we plug in 1 and then we subtract, plug in 0. Plug in 1, then we subtract, plug in 0. Had we done it in the blue one, I sometimes start by writing it out like this, okay? If I had plugged in 1, this would be 1/4 and this would be e to the 1. If I plugged in 0, this would be 0 over 4, which is 0, plus e to the 0, which is 1. And you'll notice you get exactly the same answer, right? We have the e left. We have the 1/4 minus 1, which gives us the -3/4. But sometimes the properties are nice. I find in particular, the natural log is sneaky. When you're dealing with so many power rules along the way, you see one like this and you think, oh, I'll just do another power rule. And it doesn't work. Because if you move that x to the top and get an x to the -1, if you add 1 to the exponent, you get 0, and then you try to divide by 0, things go bad. Now, the integral of 1 over x is natural log of x. This has a 5 in there, so sometimes pulling that 5 out in front really helps you see the 1 over x. Again, it is not wrong, and some of you will keep the 5 inside. Both are fine. Notation-wise, what you have to be careful with is the 5 outside means you have to put this in brackets and plug in the e and subtract and plug in the 1. Absolute values didn't matter here because we had all positive values. And on this one, it would have looked like this: 5 natural log of e minus 5 natural log of 1. So 1 is factored out, 1 would be built in. Both are going to be exactly the same. Natural log of 1 is 0. Natural log of e is 1. So we just get 5. a little crazy. I'm just saying this is a little crazy because if we think about this, 5 over x is your 1 over x graph, your 1 over x graph multiplied by 5. It would look, here's my 1 over x graph multiplied by 5. And if I look at from 1 to 2.71828188 e, under this curve, which is curving, that's perfectly fine, which is kind of crazy. That area is not close to 5, it's like perfectly 5, even though we went from 1 up to some crazy number e. That's just, I don't know. So when nice numbers come out of not nice numbers, it's sort of like, huh, kind of neat. Ooh. We do not have a quotient property for integrals. We only have a property for adding and subtracting. So a strategy that is important for grade 12 AP Calculus is something that I sometimes call unadding fractions. All through middle school and most of high school, you got really good at adding fractions. Someone said, what are the rules for adding fractions? You'd be like, I need a common denominator, then I add the tops and keep the bottom the same. So someone has done that. They've got a common denominator, added the tops and kept the bottom the same. You have to unadd them. Unadding them means that each of these could be over 4x. And if each of those was over 4x, do you see that the first one would simplify to x squared? The second one would simplify to negative 2x. The third one, if it was over 4x, would just be minus 3. And the last one would be 4 over x. So we unadd our fractions. Again, most of us eventually will just do this. Right, it is one big thing. But since we've separated it, we have to do all of these indefinite integrals. And then you plug in the top number, subtract, plug in the bottom number for each one. If there was a long answer on AP exam, I'd say stop there. Don't do any of that arithmetic. Any question that you do for me or Mr. LaFrance on a quiz, we want you to keep going and simplify. It's still good to practice simplifying because on the multiple choice, for sure it'll be simplified. They might even play with their log laws to see if you know that 4 natural log of 2 is the same as natural log of 16. And once you're done this, take a look at the next two, see if you can find the question mark. All right, the question marks. I think this first one is pretty obvious. If the area from 2 to 9 is equal to the area from 2 to something, and then from 4 to 9, the question mark has to be 4. The second one was a little trickier. Technically, there was something in our property that we did not need to have. It's just intuitive to think of it that way. When you go from the area from A to B, okay, that's going to be split up if you have a point in between the area from A to C and then C to B. C did not have to be in between. Check this out. If I make this a 16, and then I use the negative to put the 16 on top and the 12 on the bottom, then I go from 3 to 16 and then 16 back to 12, that would be the same as going from 3 to 12. But it's a little bit of trickiness there. Here we have a piecewise function. We want to find the area under the graph of the function, and the function goes from 0 all the way up to 7. So we would have to find the area from 0 to 5 under the 2x squared. And then when we go from 5 to 7, it's going to be under the 20. Each of these are simple integrals. Add 1 to the exponent and divide. 20 will just be 20x. Plug things in and solve. So if you have a piecewise function, you have to do the integral under one piece separately from the integral under the other piece. This now allows us to do integrals of absolute value functions. So initially, this next question with the absolute value of x minus 3 looks difficult because we haven't done that before. All of your skills from graphing really come in handy from grade 12. You know what the absolute value graph looks like. This is a translation of it. 3 units to the right. That's the graph. What is this question asking? This question is asking from 0 to 4, what's this area? Now, since I graphed it, I feel like, that's actually super easy to do without any integrals whatsoever. Base times height divided by 2. Do you see that this first part, 3 times 4 divided by 2, this first part area is going to be 6. And this 1 times 1 divided by 2, this part is going to be a half. 6 plus a half, I get 6.5. No integration necessary. That's great if it was a nice simple one like this. But we can write the absolute value of x minus 3. It's just 2 straight lines. The one line, very quick. The one line is negative x plus 3, or negative bracket x minus 3, and the other line is x minus 3. Because originally, if you think about x minus 3, I'll draw it here in blue, the dotted line. This is x minus 3, right? What did the absolute value do? It took this bottom part and flipped it over the x-axis. Flipping something over the x-axis is putting a negative out in front of the function. So the part to the right of 3 stayed the same. The part to the left of 3, you had to flip up, and this creates your piecewise function. When we write piecewise functions, we include the equal sign only in one of them. It doesn't matter which one you choose, but it is only in one of them. And so now we can integrate from 0 to 3 of the negative part, and from 3 to 4 of the other part. Now that we've got the answer already, I feel bad looking and doing all of this algebra and plugging all of these things in, only to get, what did we do wrong? 5. Uh-oh. I'm feeling terrible. Oh, that's because this only goes up to, I made it go up to 4, but it would only go up to 3. And then 3 times 3 divided by 2, this will be 4.5. Okay. So maybe we should do the calculus, because if we make a mental math error in our drawing, that would be bad. And terribly embarrassing. I'm okay, but that's right. That's what all math teachers do. They say, oh, I did that on purpose to see if you were paying attention. Right. Absolutely. And the fact that my face is red and my eyes are tearing, nothing to do with, it's just allergies or something. Now I'm going to say you should always do it 2 different ways, so you can check to see if your math is right. And sometimes on the AP exam, they'll just give you a picture of the graph and they expect you to do area formulas that you know. This would be a piecewise function with like 1, 2, 3, 4, 5 different pieces if you wrote it out as an equation. But if we want to find the area from -1 to -4, okay, I'm going to take out my crayon, I'm going to go purple. There it is. That's the area from -4 to -1. The area from -4 to -1 is that triangle. I can do base times height divided by 2. And I get that area is 3. I'm going to color code each of these with different crayons. I'm going to go green under here. I would probably do this as a triangle here. This rectangle. And we're going to write the area for each of these. Do you see the green part is a circle? Half of it. Area of a circle is pi r squared. So this would be pi, radius is 1. Area of the whole circle would be pi. Then the area of that half circle would be pi over 2. The orange part, base times height divided by 2. 1 times 3 divided by 2. This is 1.5. That'll make also this 1.5. And base times height. Whoops. 2 times 3. That area is 6. So now that we have all of those areas, that's going to help us figure out things moving forward. If you went from 1 to 2, oh, we've got it already labeled on there. We get 1.5. Oh, sorry, negative 2 to 1. I read it wrong. So we know that 1 to 2 is 1.5. So going backwards from 2 to 1 will be a negative 1.5. From 1 to 5, you see that you'd have to add the 1.5, the 6, and the 1.5? We should get 9. And there's a 2 in front, so that 2 gets pulled out. 9 times 2 gives us 18. If you went all the way from negative 4 to 5, you would add up all of these, but that green section, that pi over 2, which is below the x-axis, maybe you already want to label it with a negative here, because everything below the x-axis we consider as a negative area. We add up all of those sections. We're going to get 12 minus that pi over 2. Four to 2 would be the negative of 2 to 4, since we know 2 to 4 is 6. This will be negative 6. Negative 4 to positive 1 of the absolute value. What would the absolute value do? It would take that green part that was negative and flip it up and make it positive. So then I would have 3 plus that pi over 2 in the end.